Good morning, Ethicon. Thank you for bringing me and my colleagues in as consultants for polypropylene. Today, we are going to explain the chemistry of polypropylene, and we are going to discuss whether polypropylene is suitable in your product, PROLENE. We are also going to discuss how polypropylene, which is already one of the most environmentally friendly plastics, can be recycled.
Polypropylene is a widely used thermoplastic commonly used for packaging and removable plastic parts such as bottle caps, clothing accessories, and other flexible packaging. It is the second most used industrial plastic in the world, and a primary use of polypropylene is for medical suture, which we believe to be an efficient use of the plastic. Due to its relative strength, inexpensive price, and environmental benefits, it is our recommendation for the suitable material for suture.
Now, David is going to talk about the chemistry of polypropylene.
The structure of polypropylene is simple, as its repeating monomer is just a propane unit. This means that it is a large hydrocarbon made up of repeating 3 carbon units. There are no rings or pi bonds. Despite this, there are still many variations that may appear in higher levels of the structure, essentially when you zoom out. Tacticity is a characteristic that describes the alignment of this last methyl group. Wherein there is no pattern, the polymer is called atactic. Atactic polypropylene is a rubbery, amorphous thermoplastic. When each methyl group is aligned in the same direction, though, the polymer is called isotactic. Isotactic polypropylene is harder and more crystalline. Syndiotactic polypropylene is made up of alternating methyl groups. It has a lower melting point than isotactic polypropylene, but is similarly crystalline and hard, but slightly less so. For this reason, isotactic polypropylene is the best choice for structural plastics like PROLENE. There are many different types of syntheses, and each separate one is tailored for different tacticities. These all generally fall under the umbrella of Ziegler-Natta or metallocene catalysts, with many methods discovered for each tacticity. The synthesis of atactic polypropylene uses the catalyst on the screen. Interestingly, the magnesium component was discovered to speed up the reaction dramatically decades after the titanium chloride and aluminum section were used successfully for the first time. Syndiotactic polypropylene is new to commercial production, and highly stereoregular forms are synthesized using metallocene catalysts, one of which being the catalyst up on the screen again. Metallocenes are compounds which are often coordinated with 2 cyclopentene structures, and this catalyst is no different, with the cyclopentenes coordinated around the zinc. This synthesis uses this metallocene as well as MAO, or the compound methyl aluminooxane. We won't be focusing on these syntheses though, instead focusing on the Ziegler-Natta polymerization for isotactic polypropylene, as that is what we would like to use for PROLENE.
In the production of polypropylene, the Ziegler-Natta polymerization is often used. The conditions for the polymerization, with a temperature typically between 0 degrees Celsius and 100 degrees Celsius, and the pressure typically between 0.7 and 3.5 megapascals, are dependent on the different products produced. The following process of the polymerization is as follows. When titanium 3 chloride is in a crystal structure, each titanium is bonded to 6 chlorines. However, at the surface of the crystal, one of the 6 orbitals is empty. Now, the process of the Ziegler-Natta polymerization begins. The ligand diethyl aluminum chloride donates an ethyl group to the Ziegler-Natta catalyst, which is a titanium with the open orbital, removing a chlorine in the process. The ethyl group from the aluminum bonds to the titanium, filling one of these orbitals. The aluminum then forms a coordinate bond with the lost ethyl group and the chlorine in the titanium. After this step, there is still one empty orbital. Here is when propylene comes in. The propylene has a carbon-carbon double bond, so there is both a sigma bond and a pi bond. The pi electrons from this double bond fill titanium's empty orbital. Some electrons shift, creating bonds between the titanium and the carbon, and between the ethyl group to the other carbon on the propylene. The bond between the titanium and the ethyl group breaks. The atoms will rearrange, which will reveal an empty orbital on the titanium. Pi electrons in the propylene will be donated to the titanium and the process will restart, forming a chain called polypropylene. A product that is made out of polypropylene is PROLENE, which is a non-absorbable synthetic medical suture. This type of suture is produced by your company and is used by almost every hospital. The only other non-absorbable sutures out there are silk and nylon. Silk, unlike polypropylene or nylon, is not a monofilament, meaning that silk consists of many threads instead of one single one. Silk is primarily used for securing drains, for example in certain chest tubes that drain fluids or air out of the chest, whereas nylon and polypropylene is often used as a skin suture, for example closing lacerations or wounds. Polypropylene is unique because of its high plasticity, meaning that polypropylene is able to stretch to accommodate increase in tissue bulk. Therefore, polypropylene is excellent at accommodating swelling. The great thing about nylon is that it has high tensile strength, meaning that nylon can withstand a high amount of stress before breaking. In addition, nylon has slightly better handling than polypropylene. Therefore, all three non-absorbable sutures are unique in its uses, and neither are replacements for one another. I would also like to add that polypropylene is significantly cheaper than other materials for non-absorbable sutures. Polypropylene is priced at 13 cents per pound. Nylon is priced at $1.47 per pound, and silk is priced at $80 per pound. Once again, I would like to state that although polypropylene is the least expensive, price should not be a consideration. These sutures are not substitutes for one another.
Polypropylene can be recycled, which is important due to its short lifespan. There are 5 steps involved in recycling polypropylene: collecting, sorting, cleaning, reprocessing, and producing new products. The first step is to collect the polypropylene. The second step is separating the polypropylene material from other types of plastic polymers. This is usually achieved through a sink float separation technique based on polypropylene's unique density that allows it to float while other polymers sink. The third step is washing the chunks of polypropylene using specialized detergents in order to remove all contaminants. Afterwards, the chunks of polypropylene are heated to dry it off. Fourthly, the polypropylene is fed into an extruder and melted at a temperature above 400 degrees Fahrenheit. The temperature has to be this high because of the extremely high melting point of polypropylene. This leads to thermal degradation, which weakens the bonds between hydrogen and carbon in order to compromise the structural intensity of the plastic bonds. Lastly, after it is melted, it is cut into pebbles, which are used in the production of many new products such as dishware, food containers, clothing fibers, and shovels.
According to the data presented, polypropylene is clearly the most environmentally friendly. It takes the least energy to produce. It takes 73.4 megajoules to produce 1 kilogram of polypropylene, whereas it takes 138.6 megajoules to produce 1 kilogram of nylon 6,6. In addition, it takes a high amount of energy to melt polypropylene, so it will not leach and therefore is even allowed to serve as food containers.
For various reasons, we believe that polypropylene is the appropriate material for medical suture, simply known as PROLENE.
First, polypropylene is exceptionally good in several cases. In areas where the wound is prone to swelling, polypropylene is by far the best choice due to its high plasticity. Polypropylene is most often used by cardiovascular surgeons due to the low coefficient of friction, resulting in less tissue trauma. Nylon is unique due to its high tensile strength, resulting in high wound security. Plastic surgeons often prefer nylon due to these characteristics and the fact that nylon has slightly better handling than polypropylene. Lastly, silk is unique due to its uses in securing drains because of its high coefficient of friction. Silk is not often used in skin closures due to its low tensile strength and high tissue reactivity. Second, polypropylene is recyclable and takes less energy to produce. Therefore, it is significantly more environmentally efficient than nylon and other plastics. Third, polypropylene is reasonably priced, being more economically friendly than other materials such as nylon. Thus, we would like to conclude that polypropylene is a reasonable material for producing sutures. Although polypropylene is an excellent plastic, surpassing other materials like nylon and silk in many categories, polypropylene is not a substitute for other materials because every single material has its unique uses and different circumstances require different sutures.